Once you're able to make predictions about how much product should be produced in stoichiometry, then you can move on to the concept of percent yield. So that question is, what is percent yield when it relates to chemistry? Well, it's just a way to be able to compare what you're actually producing, so what you're actually gathering in an experimental or laboratory situation over the theoretical, like what you had predicted that you would produce. So that's based on the calculated values. That's what you're using stoichiometry for. So typically in these problems, you're going to be given the mass of a reactant, and you'll be asked the mass of the product. Then it'll say this is how much you actually collected in lab, and you'll just do a comparison of the actual over the theoretical you calculated. And because it's a percentage, you'll multiply that by 100. Now you can work your way backwards. So some of the more advanced problems would give you the percent yield. So they'd give you the actual number. They might also give you the theoretical or actual yield. And then they would actually ask you to work backwards and figure out how much product you must have started with. So it's a little bit more of a complicated variation, but definitely something that you're capable of solving. So for this little tutorial here, I just want to walk through one example problem of calculating out percent yield using limiting reactants. So this is another thing that you might come across, is where you have an equation where you have to determine the limiting reactant first, then base your theoretical yield of potassium chloride, for example, off of that limiting reactant, and then go through that process. So we'll go ahead and do that. It's a good review of what you already should know how to do at this point. All right, so the very first thing we're looking at here is an unbalanced equation. So let's start by balancing that out to begin with. So if we look at FeCl3, there should be a 3 in front of the KCl, which means that there should be a 3 in front of KOH, and then our hydroxides are balanced along with our irons. All right, so I know that I need 3 of those potassium hydroxide, like 3 moles of that for every 1 mole of FeCl3. I also know that FeCl3 has a higher molar mass in comparison, and I've got more potassium hydroxide. So my guess here is that iron 3 chloride is going to be my limiting reactant, so I'm going to just work the problem with that in mind. So starting off with 5 grams of FeCl3 over 1. I'm going to divide by the molar mass here in the next step. So having calculated that out already, it's 162.20 grams. Now I am going to compare this directly to the product, and then I'm also going to go back and do the same thing for the potassium hydroxide. The other thing I could do is compare the iron 3 chloride to the potassium hydroxide the way that I've done it in the past to confirm that FeCl3 is my answer, but this will actually hopefully save me one tiny little step in the end here. All right, again, I'm going to go from FeCl3, which there's 1 mole of that, to the moles of KCl. Lots of different ways you can tackle these problems. Oops, I need to do one more step. I must hit an equal there because I need to know how many grams are being produced. So 1 mole of KCl has a molar mass of 74.55 grams. All right, and I'll do that calculation here quickly. So 5 divided by 162.20 times 3 times 74.55 will produce a maximum amount of 6.89 grams of KCl. Again, we have to determine which is the limiting reactant amount, and then we can do our problem from that, go from there. So I'm going to start off my next section with the KOH, and again, just determine how much KCl. So starting off with 15 grams. Multiply by the molar mass of, or sorry, not multiply by it, but divide by the molar mass of KOH. Multiply by the mole ratio, which ends up being a 1-to-1. So 3 moles of KOH will produce 3 moles of potassium chloride. And then finally, how many grams will that release? Oops. Wrong compound. So KCl, 74.55 grams of KCl. All right, plugging that into the calculator, 15 divided by 56.11. The 3's cancel out, times 74.55. This would produce 19.9 grams of KCl if it was completely consumed. And so we know then, looking at the two and kind of comparing, that my FeCl3 is going to produce my maximum amount of potassium chloride. So the maximum amount would be 6.89 grams. All right, so that would be my theoretical. Now, in this problem, they would have given us what the actual value would have been. And for this particular problem, let's say that we actually were able to get back 5.50 grams of KCl. So we're just taking the actual divided by the theoretical. And that gives me, I'm going to multiply that by 100 just to give the percent. So that would give me 79.8%, which is actually a really great percent yield for a reaction, because there's a lot of things that can go, I don't want to say wrong, but that can go astray in running an actual chemical reaction. Number one, your conditions might not be right to produce 100%. Number two, there are oftentimes side reactions that are occurring in this process. So other things that are involving the chemical products or the reactants themselves, which are reducing the amount of product you might get. In some situations, things might be decomposing as they're being produced. This wouldn't be an example of that. There's just lots, human error and all those other kinds of things, impure samples that could make these numbers lower. So a percent yield of 79.8% in an actual lab would be a fairly great amount for this kind of reaction. All right, again, limiting reactants oftentimes come into play with the percent yield, but the biggest thing that you guys need to focus in on is do the stoichiometry that you know how to do, the grams to grams. Once you have calculated that out, again, that is your theoretical yield. That's why you're doing the stoich. Typically, the experimental values in these problems will have been given to you. If you were in lab, you would be running these chemical reactions, you'd be isolating those products, and then you would do a comparison between what you calculated you should have gotten and what you actually were able to retrieve. So lots of advanced kind of topics and techniques happening in these problems in real life. All right, the practice that you guys are going to do is going to focus basically on, more of the limiting reactants, and then at the end you're just calculating out percent yield. So hopefully it's a pretty straightforward process.